today's lesson, we're going to talk first about isotopes, and then we'll get into some mathematical calculations that we can do. So we learned the other day that an ion is something that has gained or lost electrons. And so they're going to end up with a charge. So we think this all things like calcium 2 positive, which means it's lost 2 electrons. Another I word is isotope. Isotopes are atoms of the same element that have different number of neutrons. And because neutrons are built into the atomic mass, they're also going to have different mass. So an example of some isotopes. So we have hydrogen 1, we also have hydrogen 2, and we have hydrogen 3. They're all hydrogen, but they have different masses, and the reason is because they have a different number of neutrons. The protons are the same. So if we were to look at some isotopes in nuclear notation, if I had 3 isotopes of hydrogen here, each of them has 1 proton, because that can't change. If that changes, then the identity of the element changes. So we have all of them with the atomic number 1 here. They have the same number of protons. Hydrogen 1 has a mass of 1, which means it has no neutrons. Hydrogen 2 has a mass of 2, and hydrogen 3 has a mass of 3. And so that's what they would look like in nuclear notation, the difference of the isotopes. All right, so now we're going to learn some calculations, and these calculations involve 2 different conversion factors. So before I get to those, we've got to talk about, so we're going to be relating mass to the number of atoms. We have to talk about this concept of a mole. A mole, and I generally will use this abbreviation. I don't know why they needed to abbreviate a 3-letter or 4-letter word with a 3-letter word, but they do. Proper, it does have an E, but an accepted abbreviation does not have the E. I generally will use the term without the E. This is based on carbon 12. And that's a pretty important element for us since that's what we are made up of. And it's as many atoms as there are atoms in 12 grams of carbon-12. It's the legal schmeagle. But basically this is a unit of measure that you just haven't heard of before. We'll use it all the time in chemistry, so it is a very essential unit of measure for chemists. Now, let's go to conversion factors. We have Avogadros number, and that's going to relate atoms to moles and moles to atoms. When you have a number with 2 units there, we are going to use it as a conversion factor, and you can always read this line as N1. So there are this many atoms in 1 mole. Another way to write that would be 6.022 times 10 to the 23rd atoms equals 1 mole. So we're going to be working with that here in a little bit, but before we get to working with Avogadros number, we're going to use the conversion factor molar mass. Molar mass is sometimes called molecular weight, and it's found on the periodic table. I will exclusively use molar mass, though, in my class. Units for molar mass are grams per mole. So again, we have 2 units in the conversion factor, so that's what we're going to use it for. We can go from grams to moles or moles to grams. Now, it is found on the periodic table. If we look at our periodic table, where we're going to find our molar mass is this bottom number right here. And I always take it to 2 decimal places. So I would say this one's 6.94 grams per mole, and you just put those units on there. It's different for every single element. You'll notice sodium is different than lithium, which is different than beryllium. You will need to use your periodic table so that you can find what the elements are. All right. Here are a couple of examples. You can see I wrote these just written off the periodic table. Lithium, there are this many grams of lithium in 1 mole of lithium. So we can also write it this way. 6.94 grams equals 1 mole of lithium. And this is mercury, Hg, number 80 on the periodic table. And it has a molar mass of 200.59 grams in 1 mole. And again, this converts from grams to moles or moles to grams. Now, calculations using molar mass. First one is, what is the mass in grams of 3.6 moles of carbon? So, what we are going to do with this one is, I'm going to start my dimensional analysis with the number given in the problem. There are this many moles of carbon. I need to go from moles to grams. So the conversion factor that goes from moles to grams or grams to moles is molar mass, and we find it on the periodic table. So I need to look up carbon on the periodic table, and I can see that its molar mass is 12.01 grams per mole. So I'm just going to write that down. We'll use that in a second. 12.01 grams per mole. Now, I'm going to convert moles to grams using this conversion factor. Mole is here, so mole has to go here. And what this conversion factor says is there are 12.01 grams in 1 mole. So in 1 mole, there are 12.01 grams of carbon. Moles cancel out, and I'm just left with grams of carbon. Remember, we only base our sig figs off the number given in the problem. So for this one, I need 2 sig figs. You multiply everything on top together and divide by everything on the bottom, multiply together. So I get 43 with those 2 sig figs. Okay, this is the same type of problem, so if you're learning this for the first time, you can pause this screencast, and then you can try this one and make sure that you've got it. So we have 5.23 moles of phosphorus. So 5.23 moles of phosphorus. Phosphorus is P. We're going to need to go from moles to grams, so we're going to have to use our periodic table. And for phosphorus, I find that the molar mass is 30.97. So there are 30.97 grams, 30.97 grams per mole. Mole is here, mole has to go here, so they will cancel out. And this says that there are 30.97 grams in 1 mole. So in 1 mole, there are 30.97 grams of phosphorus. Answer. We multiply everything on top together, divide by everything on the bottom, multiply together. We know we need to have 3 sig figs. Always go back to the problem for your sig figs. And in this one, we end up with 162 grams of phosphorus. Alright, we're still working with molar mass. In this particular problem, it's just a little different. This time we're starting with grams, and we're going to go to moles. So we're still going to be using molar mass, and be careful that you actually look at the name on the periodic table and make sure you have the correct substance, because CO is cobalt, not copper. Alright, so I have 3.22 grams of copper. Since I'm going from grams to moles, I need the molar mass. So I'm going to find copper on the periodic table. It's right here. That's how many grams are in 1 mole, 63.55. So 63.55 grams per mole. Gram is here, so gram has to go here. And there are 63.55 grams in 1 mole. So the number that you get from the periodic table is tied to the grams, and you cannot move it from there. And it's always going to be for 1 mole. Grams cancel. Everything on top is multiplied together, divided by everything on the bottom. We need to consider sig figs. The number given in the problem has 3 sig figs, so we need to have 3 sig figs in our answer. So leading zeros are not significant. And then you want to make sure you round properly. So now it's 3 sig figs, moles of copper. Right? Again, if you're watching this for the first time, you may want to try this one. So you can pause the screencast right now. Alright, we have 224 grams of potassium. And potassium is K. Again, you have the periodic table with the names on them. And we're going to convert that to moles. So we're going to go from grams to moles. So we need to use molar mass. So we find potassium. Potassium is right here, 39.10 grams per mole. So 39.10 grams per mole. Gram is here. Gram has to go here. And again, that number is tied to the grams. So 39.10 grams in 1 mole of potassium. Grams cancel. All I'm left with are moles of potassium. And for that one, we are going to need 3 sig figs. So it's going to be 5.73 moles of potassium. So that's working with molar mass, converting from grams to moles or moles to grams. Now we're going to work with Avogadro's number. Avogadro's number is given to you. It's 6.022 times 10 to the 23rd atoms per mole. And again, it will convert atoms to moles and moles to atoms. This number is not one you have to memorize. It is given to you. To know when you have to use Avogadro's number, our key word is the word atoms. If you see the word atoms anywhere in a problem, you are going to have to use Avogadro's number somewhere. So, in this particular problem, we have 2.00 times 10 to the 6 atoms of oxygen. And we want to convert that to moles. Well, I see that word atoms right here, so I know I'm going to have to use Avogadro's number. We want to ask ourselves, can I go ahead and use it now? If the thing in this spot has the units of atoms or moles, then the answer is yes. So, here I have atoms, so yes, I can use Avogadro's number, so I'm going to. Atoms are here, atoms have to go here, and so it's 6.022 times 10 to the 23rd atoms in 1 mole. Again, it's going to be in 1 mole. Do not, that word atom is tied to this number. Now you're going to plug this into your calculator. You want to make sure that you're using the EE button correctly, so I'm going to show you what it's going to look like in your calculator. So we have 2.00, and then you're going to hit the EE button. And that's what I'm talking about, this EE button. It just comes up with 1 E on your calculator. And then that means times 10 to the 6th. So I've just entered in this number. There's no times, no 10, no up here. The EE takes care of it all. Then divided by 6.022. Again, EE 23. Now, when you get the answer, and a lot of times this is the case, in answers with using Avogadro's number, it's generally going to be in scientific notation. So make sure you take the time to look all the way to the end of your calculator. In this particular problem, we need 3 sig figs, because that's how many I have right here, and it's 3.32 times 10 to the negative 18 moles of oxygen. Alright, this next one is similar, still going to use Avogadro's number, and we know that because we see the word atoms here. This time we're starting with moles instead of atoms. So, write down what's in the problem, 5.010 moles of copper. Again, we saw the word atom in the problem, so we know we're going to have to use Avogadro's number. We want to ask ourselves, can we use it now? Well, I told you if it has either atoms or moles, you can use it now. This one has moles in this spot, so yes, we can use Avogadro's number. Mole is here, mole has to go here, and in 1 mole, there are 6.022 times 10 to the 23rd atoms of anything, and this time we're talking about copper. So, we're going to multiply everything on top together, divide by everything on the bottom, multiply together, and our answer will be in atoms, because moles cancel out. We need 4 sig figs, so 3.017 times 10 to the 24 atoms of copper.